So hello my dears, now we are going to look at full wave rectifier. Okay, full wave rectifier. So this is nothing but the input wave, input supply, input AC supply. Okay, this is nothing but the transformer. So listen my dear, so what is meant by full wave rectifier means full wave rectifier. It converts the entire input cycles of the waveform that we are applied. That means both positive half cycle and negative half cycle, the rectifier will produce the output voltage. That is called the full wave rectifier. So let us discuss the working symbol, and you don't know this already, I know. So for positive, we are using a center tapped transformer. This is nothing but my center tapped transformer. So use as center tapped transformer. So what is mean by a center tapped transformer is nothing but, my dear, normally a transformer, a transformer having a whole voltage of Vm, you imagine the whole voltage, suppose a transformer having Vm. In a center tapped transformer, we are adjusting the number of turns in such a manner that if you take exactly the center of the winding, secondary winding, then the first half will produce Vm and the second half will produce Vm. That means for a normal transistor, if you take the number of turns in the secondary as 100, suppose say a number 100, but in a center tap transformer, you should take the number of turns as 200. Then only it will produce Vm and Vm in the both positive and second half cycle. Okay, this is a simple logic. So for positive half cycle, what happened, my dear? The polarity will be in such a manner, this will be plus and this will be minus. We know that, right? The terminals, polarity of the secondary winding of the transformer will be plus and minus. And the center portion is always zero potential. So it will mean this is plus, mean this is minus, and this will be plus. That's all. That is concept of zero potential at the center. So what happened to the diode D1 and D2? Now let's discuss. So for diode D, it is plus and its P means it will be forward biased. So what happened? The Vm supply that is completely transferred to this RL. So the whole of the Vm sin omega t that we are applied will be available to the output due to diode D1, that is N D1. At the same time, my dear, this is N and this is P. This is negative and this is positive. What happened? The diode D2 will be reverse biased, but there will not be any output voltage produced by D2, simply it acts as an open circuit. That means it seems like only this one, that is a half wave rectifier circuit, it seems like. Okay, and for the negative half cycle, this is the supply, this is the positive half cycle term you explain now. For next, this negative half cycle, what happened? The polarity will be like this. This will be plus and this will be minus. And the center will be nothing but, my dear, plus and minus. That's all. All over it's zero, all over it's also zero. So what happened, my dear? The diode D2 get P and P, so it is forward biased, but it is get negative to P, so it is reverse biased, so it is simply act as an open circuit. So the whole of the Vm sin omega t is available across the load resistors. In both the cases, my dear, this is the current direction now. This is the current direction now. So what we can conclude? The current is flowing in same direction in both of the cases across the RL, so that the current output will be unidirectional. The current output will be unidirectional. Okay, this is the simple working of this transformer. The term you have to note, very very important term, is nothing but, my dear, peak inverse voltage. Many competitive examination this question is asked. What is the peak inverse voltage of a center tapped rectifier circuit, full wave rectifier circuits? The answer is 2 Vm. How it is obtained, I will discuss. I will tell you now. See, my dear, so I already told you what is mean by a peak inverse voltage is nothing but a reverse voltage. Whenever the diode is reverse biased, what its terminal voltage, that is called the peak inverse voltage. Let us check. For positive half cycle, this is forward biased, at the same time this is reverse biased. So this is reverse biased, let us open this. Let's open this. So this term voltage, this is nothing but, my dear, peak inverse voltage. So V peak inverse voltage, PI, V PAV. Okay, let us denote as VPAV, peak inverse voltage. Then what is the voltage now? What is the voltage now? What is the voltage now? Voltage, if you take a voltmeter and measure the voltage between these two terminals, what are the voltage you obtain? See, from here to here you will obtain -2 plus Vm. Again from here to here -2 plus Vm. Correct na? By basic voltage law, Kirchhoff voltage law. -2 plus positive, -2 plus again positive. So plus Vm and plus Vm will be available across these two terminals. Am I right, my dear? Is it very easy? It is easy now. So if you measure the voltage between these two terminals, means I am tracing. Tracing can be any direction, no problem. I am tracing from here to here. For positive half cycle, this is the polarity. You have to note that. Next negative half cycle is this is the polarity. Okay. For positive polarity, what is here to here? Negative to positive, increasing voltage Vm plus Vm. Again from minus to plus, again increasing voltage plus Vm. So total voltage is nothing but 2 Vm. That is very, very important. And next is also very, very important, my dear. The output frequency is nothing but 2 times the input frequency. This is the input waveform. This is the input waveform. And this is the output waveform now. This is the output waveform now. So pi to 2 pi, and this is 3 pi. So 2 pi only, the waveform, input waveform repeats from 2 pi only. So the total time period is 2 pi now. But see the output waveform, the cycles are repeat from here itself, it's repeat. That means from pi itself the cycle is repeated. Okay, that means from 0 to 2 pi in the input side it only complete one cycle. Only after this it's repeating. Only after this it's repeating. But in the case of the output waveform, it's repeat after every half cycle it is repeating. Every half cycle of the input voltage, my dear, it's repeating. So compared to the input voltage, the output oscillates twice as that of the input frequency. The output oscillates twice as that of the input frequency. Am I right? Am I right, my dears? Am I right? That is why the output frequency is nothing but 2 times the input frequency. Now use a center tapped transformer, that is already explained. But it has certain disadvantages compared to the half wave rectifier. Also advantage also there. What is the advantage? Full wave rectifiers. What is the advantage? Full wave, how you can produce, right? Full wave you can produce. So let us see the efficiency also. Okay. Then you will learn somewhat a clarity. You will get a clarity there. Efficiency. Mainly we are dealing with rectification efficiency. Unless it is mentioned power efficiency, you don't worry about power efficiency. Simply mean for rectification efficiency. Okay. So rectification efficiency, my dear. So efficiency simply means for rectification efficiency. So efficiency is nothing but, my dear, PDC divided by PAC. So what is PDC? It is nothing but IDC the whole square into RL, which is nothing but, my dear. What is IDC now? For full wave rectification, you can substitute the value of, again, IDC is nothing but, my dear, I will explain that also. IDC is nothing but, my dear, again 1 by 2 pi into integral 0 to 2 pi. Okay, time period for full wave rectifier is nothing but 1 by pi and 0 to pi. Correct? 0 to pi. 0 to pi. Im sin theta. If you solve it, you will get like IDC equal to 2Im by pi. Okay, IDC equal to 2Im by pi. Okay, and what is PAC? PAC is nothing but, my dear, IRMS the whole square into RF plus RL. Same thing, no change in that. So what is IRMS now? IRMS is nothing but full wave rectifier. What is that? Im by root 2. Am I right? For full wave, for a full wave, it is Im by root 2. Am I right, my dear? It is Im by root 2. Am I right? Correct. Im by root 2. Now you know this, right? Im by root 2 into RL. Okay. It's not RL, it's simply IRMS, na? Simple that. Im by root 2 only. So what is PAC now? PAC is nothing but Im by root 2 the whole square into, what is that? RF plus RL. Is it clear, my dear? So this is PAC and this is PDC. Okay. So what will be the efficiency now? Efficiency eta will be equal to PDC. Output is nothing but 2Im divided by pi na. 2Im divided by pi the whole square into RL whole divided by, again this is Im by root 2 the whole square into RF plus RL. Again, if you can take RL outside and you can cancel, and finally you will obtain like percentage efficiency will be equal to what? 4 divided by pi square into 2 divided by 1. Okay, so it is simply like 8 divided by pi square into 100. So there were 4 divided by 5 square, now it is 8 divided by 5 square. So efficiency will be approximately what, my dear? 40.6 will become 81 nearly, right? Or 80.2. Okay, any value you can write. 81. 81.2. 40.6 will become 81.2%. This value is very, very important. This value is very, very important. That is the full wave rectifier efficiency for what? Center tapped. Okay, center tapped. Next, another type of rectifier is also there, which is called a full wave rectifier is also there. Bridge rectifier. Now we learned about the center tapped. Na? Similarly, another type of rectifier is also there, bridge rectifier. That also we will going to discuss. Bridge rectifier. Okay. Just a minute. Okay, that's opposite now. Yeah. Here also. Yes. Okay. D1, D2, D3, D4. So this is the circuit diagram of a full wave bridge rectifier, my dear. Okay, full wave rectifier, bridge rectifier. The output will be same. There is no problem. We will discuss that. Okay, we will discuss. So this is the AC input waveform. Input AC supply. Okay, so this will be the input AC supply. So for positive half cycle of the input AC supply, my dear, the polarity will be like this is plus and this is minus. So this is minus mean this terminal will become minus, and this is plus mean this terminal will become plus. So what happened? Due to this plus, this will be forward biased. Now this will be forward biased for positive half cycle. For positive half cycle, what is that? For positive half cycle, D1, this will be forward, this P to connected to P, positive to connected to P, so D1 will be forward biased. This negative will be connected to this negative N, so D3 also forward biased. So D1 and D3 on, am I right? D1 and D3 on or forward biased. So what will be the supply nature? The supply will come from, see, the supply will come from like this, here to here, and it comes like, see, I will draw. It will come like this one, and it will come to earth. It will come to earth. Earth and earth are connected common, so it will come, it will rise, uprise. It will come like here. So D3 is on now, so it will come like this. It will come like this, and it will complete its path. So it start from here, my dear. It start from here, and it come like this. It is connected, so it end here, it start here. Start here and come like this, come like this, come like this, and it completes. So what happened, my dear? D1 and D3 will be forward biased, so you will get the full positive half cycle as the output waveform. So the output waveform is nothing but, my dear, so this is the input waveform. So the output waveform is nothing but this positive half cycle obtained, D1 and D3. This is V input, this is V output, simple. Okay, and for negative half cycle, what happens? For negative half cycle, what happened, my dear? For negative half cycle, my dears, this will be minus and this will be plus, am I right? For negative half cycle, the polarity will be reversed. So this will be minus and this will be plus. This plus means here it is plus. This minus means here it is minus. So what are the terminals will come forward biased? Due to this plus, D2 will become forward biased. Due to this minus, D4 will become forward biased. Now this minus and N will be connected, right? So D4 will be forward biased. So I could write like for positive half cycle, and here itself I like for negative half cycle, D2 and D4 on. Am I right, my dear? D2 and D4 on for negative half cycle. Is it correct? So what happened? What will be the supply nature? So this is plus now. The current will be start from here. I know. Start from here, come here, and this is forward bias, right? So it will come like this, D2, and it will come to the earth like this. Earth and earth will be connected again. So this will come and is up like this, my dear. It will up like this, and here and it will be up like this. It will be up like this. It will come here. D2 and D4 is forward bias now, so it will come like this. It will come like this. It will come like this. And here nothing but simple. Okay, both direction you should learn. So in forward bias, I mean in positive half cycle, this D1 and D3 will become forward biased. Negative half cycle, D2 and D4 will become forward biased. So the negative half cycle also a beautiful thing you can obtain here. Both the forward half cycle, positive half cycle and negative half cycle. See the direction of the current here. This is the direction of the current. See the direction of the current here. This is the direction of the here. Is there any change in direction across this RL? From this RL we are obtaining the V output, my dear. Is there any change in the direction of the current through RL? No. In both the same half cycle, the current direction is same. That means for D1, D3 and for D2, D4, the waveform is similar. That means the current is same. The current is not reversing. The current is not changing. Again, this will be D1 and D3. So these will repeat. These things will repeat. So this is for bridge rectifier. So what is the difference from that center tapped to bridge rectifier? Only in terms of course we know that it requires 4 diode, there requires only 2 diode. It's a simple thing, you learned that. But a very important thing for examination point of view is nothing but, my dear, here The F output also same as the 2 into F input now, that you already know. But what is the peak inverse voltage now? Peak inverse voltage is what, my dear? What is this peak inverse voltage? That is going to discuss now. Okay, I am going to rub this. I'm going to rub this. Because the term peak inverse voltage is normally repeatedly asked in the examination. That's why I am giving more importance to that term, my dear. That's why I am giving more importance to that term, peak inverse voltage. Okay, so see, my dear, for the I am removing this red line because for replacing peak inverse voltage, this is somewhat annoying. Somewhat annoying, so I am going to replace this current direction. Okay, now it's clear. Okay, now it's clear. Listen, my dear. So again, what is the peak inverse voltage? Now, peak inverse voltage is nothing but the voltage available across the diodes when it is reverse biased. So for positive half cycle, what are the diodes? Should be forward biased. D1 and D3 will be forward biased. Am I right? So I can replace this D1 and D2. I will repeat it again. Okay. So okay, simple figure like this. Yeah. Okay. Okay, my dear. Okay, leave it. And this is the supply. Okay, that only we need. Listen, my dear. So across the supply, what is the voltage? Vm. Across the supply, what is the voltage now? It is Vm only. There is no change in that. So for positive half cycle, this D1 and D3 will be what? This I will mark now. D1, D3. D2 and D4. Am I right, my dears? Am I right? Yes, correct. So for positive half cycle, my dears, D1 and D2 will be forward biased. So forward biased means I can mark this, or I can simply represent like this as a short circuit, right? If you are considering an ideal diode, means you can consider like a short circuit path. So across the supply, it is equivalent to, my dear, it is equivalent to is a short circuited, so it is like am I right, my dears? It is similar, the same figure is represented like this now. So what is the voltage across this D2 and D4 now? Same Vm. Am I right? For negative half cycle, the same thing will happen, but instead of this, it will D1 and D3. That's all. Only that difference. So what will be the peak inverse now? Only Vm. This is important. This is important, my dear. For examination point of view, this is important. And efficiency and all same, 81.6. Am I right? 81.2. Efficiency is same. Efficiency is nothing but 81.2%. There is no change in at all. Okay, that's all about the full wave rectifier for examination point of view. For examination point of view. Is it clear, my dears? Is it clear? So that's all about the. That's all about the. Next, very important term in the examination point of view is nothing but, my dear, ripple factor. Factor. So what do you mean by ripple factor, my dears? Ripple factor is nothing but, my dears, RMS value of output DC, RMS value of AC component, you can write RMS value of AC component divided by DC component. This is the definition of a ripple curve. I mean, ripple is nothing but, my dear, the output is not at all a perfect straight line, but it contains this line. This is called as ripples. This is called a ripple. A ripple means it is not a straight line, but it is oscillating in nature. It is called a ripple. So the ripple factor is nothing but how much a ripple is in the RMS value of AC component. This is a ripple now. This is the RMS value. That's all. This is AC now. This is the RMS value. The effective value of AC is nothing but the RMS value. So the ripple factor is nothing but how much ripple in the output divided by pure DC component. How much ripple in the output divided by the DC component. So how much ripple means how much RMS value of AC component divided by DC component. Okay, that is the ripple of factor, I mean definition. But for examination, I mean for solving problem, this definition is not that much sufficient. We have to discuss one more thing, my dear. So total the RMS value, the effective RMS value of any waveform. See, this is the output waveform now, but practically, I mean, ideally what it should be? Ideally it should be a straight line. That means this contains, this is equivalent to what, my dear? This plus this. Am I right? This is equivalent to this plus this. That means the RMS value here in the effective output waveform of full wave rectifier is nothing but, my dear, root of IDC the whole square plus IAC the whole square. Am I right? Normally what we are doing in the general equation, see, suppose the waveform is represented V is equal to 2 plus Vm or 2 plus 4 sin omega t. Suppose you have a question like this, then what will be the RMS value? You will take like 2 square plus 4 by root 2 square na. So it's Vm na. So Vm by root 2 square will be the RMS value. This you will do na. This you will do na. Same thing is here. IDC square is IDC square. IAC is nothing but IRMS. So IRMS, that is the IAC. 4 by root 2, this is simply IAC the whole square. That's all. That's all. Okay. So from this, what is IAC? Because we need RMS value of AC component we need. AC component we need. So what is AC? It is the total RMS value. But we need RMS value of AC component only. That means the AC component, this is, my dear. This is only, this RMS value only we need. Not the whole RMS value we don't need. Only the RMS value of this we need. So IAC will be, now from here the IAC will be nothing but, my dear, root of IRMS square minus IDC square. Am I right? Am I right, my dear? IRMS square minus IDC square. Am I right? So that is IAC. So if you take IRMS, correct na? Yes. So this is IAC. So IAC divided by IDC is nothing but our ripple factor. Am I right? Ripple factor, which is nothing but, my dear, root of this one, IRMS square minus IDC square whole divided by IDC is nothing but, my dear, simply what? IDC, simply IDC. I will write like IDC. Inside the root it will come like IDC square. It is outside the root na, so inside the root it will be IDC square. So it will become root of IRMS divided by IDC the whole square minus 1. This is the equation of our area of concern. Root of IRMS by IDC the whole square minus 1. Just remember this equation only for problem solving. IRMS by IDC the whole square minus 1. IRMS by IDC the whole square minus 1. Root of IRMS. This is very, very important relationship. IRMS by IDC, root of IRMS by IDC the whole square minus 1. So ripple is nothing but, my dear, RMS value of AC component. That means the whole voltage will contain AC plus DC. So we need only the RMS value of this, that's called the numerator, and this is the denominator. That means this by this is called the ripple factor. Simply, this waveform contain this and this, so this by this will be the ripple factor. This is nothing but what? The RMS value of AC component. RMS value of AC component can be general AC component. RMS value is nothing but, my dear, that means this RMS is nothing but, my dear, for this waveform. This RMS equal to root of the DC component here square plus AC component square. So from that only AC we required. So that AC we change here. So IAC will be equal to root of IRMS square minus IDC square. Am I right? Squaring both sides. What if IRMS square equal to IDC square plus IAC square? So only IAC square is IRMS square minus IDC. Simplify this, you will get the answer. Nothing. That's all. Concept wise you have to learn, my dear. Concept is very, very important. This concept, I think it's new to you, right? It's new to you. It's new to you. In my classes, no one taught me like this. Okay, I found my own way for understanding, better understanding. Okay, the teachers will simply take IRMS by IDC the whole square minus 1. This definition they will tell and they will go. You have to learn. We have to find out our own way in order to remember that. But that should be logical. Okay, in any way you can remember anything, but according to logic only. That is the power of an engineer, right? Engineer doesn't by heart anything. Engineer doesn't, they don't want to by heart anything. They will think only if, or they will by heart, or they will learn only if there is a logic. That is the power of engineer, right? So I hope you are all engineer, all are engineers. So that is the expression for ripple factor, my dear. So that is the end of the session. So let's meet again. Thank you.